Hi everyone. In the previous chapter, you learn about atoms, right? You learn about the subatomic particle that resides within an atom, such as proton, neutron, and electrons, right? In this chapter, we are going to focus our attention on the location of electron within an atom, or what we call electronic structure. The reason why we need to know the electronic structure, because the electronic structure of an atom is going to be the one that involved with the chemical reaction. For us to understand the behavior and property of electrons better, we will first need to look at light, because electron and light are share similar properties. Okay, so and also in order to study electron, we also use light to study electron as well. So show here is the study guide for chapter 3. Okay, so we're gonna start with learning about the property of light as wave and also as particle, and then we're gonna take a look at the basic model that describe electronic structure of atom, which is called Bohr model, and then we'll get into more recent model that use currently, right, which is quantum theory. Okay, so we're gonna take a look at how quantum theory describe electron within an atom. Okay, so please read the OER textbook, chapter 3 for more detail of this chapter. Okay, so pretty much my video is going to be the summary of the OER textbook. If you want to know more detail of each section, I highly recommend you to actually read the text. You will get more detailed explanation from the textbook. Okay. All right, the homework that associated with this chapter will be assigned as paper homework. The reason why I have to assign the paper homework for chapter 3 because Newton homework have a slightly different focus than what we discuss in class. Okay, and I want your homework to align with what I teach in class and also align with the exam as well. So that's why I have to assign the paper homework. I highly recommend you to actually do homework, because without doing this homework, you will not be able to do well on the exam. Okay, so from the statistic that I observed from the past few years, right, students who complete the paper homework and check their work against the solution here, they perform better than those students who did not do homework problem at all. Okay, so, and here is how you access the homework. Okay, so click on this link right here. It's going to bring you to the homework file. You have two options. One is to download this homework and print it out. Second one is, if you don't have a printer or you don't have any way to print it, you can also provide your work and answer in blank paper as well. Make sure that you label number clearly and also write your name on it as well. Okay, so, and this is what the homework file look like. Okay, so there will be 25 questions, 7 pages that cover chapter 3.1 to 3.5. Okay, so start working on each chapter section as soon as you finish the lecture video. Okay, so after you finish, then you scan your work or take a picture and then upload it into this add submission right here. Okay, so then click submit. After you finish, when this homework solution become available, I would like you to actually click and check your work against my solution. The reason for that is because your homework is only grade based on completion and also the work shown. Okay, so the reason why I don't grade based on correctness is because it's just a practice for you, right? I don't want to penalize your work yet if it's incorrect, because it's just a practice. Okay, so just make sure that you check your work against my key. Okay, so don't forget to do that. Okay, so and also if you have any problem at all, or if your work doesn't match with what I have, just do not hesitate to reach out to me. All right, let's start with the first chapter section 3.1. Okay, so we are going to take a look at light as wave. And again, as I mentioned, the reason why we need to take a look at light first, because in order to study the electron, right, we use light to study electron, and also light and electron share similar property as well. Okay, so note that after you finish this chapter section, you should start working on paper homework chapter 3, number 1 to 6 right away. Okay, so start working on that right away. All right, so from the previous chapter, you learn about the development of atoms, right? You learn from like Dalton atomic structure all the way to Rutherford nuclear model, right? So in this case, you also read the assignment as well of chapter 2.1. And this is the solution of the reading assignment that I assign you to do, right? So make sure that you check your work against my key here, okay? So if you have any question, again, don't forget to like reach out to me, okay? And I'm going to go over the summary of this theory from the reading assignment briefly. Okay. first idea of atoms come from John Dalton, right? So he used the law of definite proportion and also the law of multiple proportion and other systematic observation to help him, right, come up with this idea of atoms. So pretty much he described atom as indivisible, right, and all matter made of atoms. Later, we discovered that this indivisible idea of atom is invalid because atom also contains subatomic particles as well that are smaller than atom itself, right? Also, atoms of the same element are identical in mass and property, and later this is also invalid as well because we see isotope before, right? So isotope of the same element, right, they have different mass. Atoms combine in simple whole number ratio to form compound. That's still valid, right? So for example, if you're looking at water, H2O, right, it have to be in a whole number ratio between hydrogen and oxygen, right? Atoms of one element cannot change into atoms of another element in a chemical reaction. This is still valid. Okay, so chemical reaction will not be able to change the identity of an element because we are not changing the number of proton. The first subatomic particle was discovered by J.J. Thomson through the cathode ray experiment, and that is the electron. Okay, so from the cathode ray experiment, he discovered a negatively charged particle, which is called electron, and he discovered that electron has mass, and he can also obtain the charge to mass ratio of the electron as well. Later on, Millikan conduct oil drop experiment and use the charge to mass ratio of electron that discovered from J.J. Thomson to deduce to get the charge and also to get the mass of electron. And it turned out that the mass of electron is a lot lighter than the mass of hydrogen gas, which is at the time, right, is the lightest atom that they know. The result suggests that electron is smaller than an atom. Therefore, electron would be subatomic particles. J.J. Thomson also proposed the plum pudding theory of an atom as well. His theory suggests that electrons are embedded within the sphere of positively charged matter, as you see here. Right? So the three dimension of his theory look like this raisin cake, right, where the raisin is pretty much represent electron and everything else represent positively charged matter. Later on, Rutherford decided to go for an experiment to validate the plum pudding theory. So in his experiment, he proposed that if this plum pudding theory is correct, then when the alpha particle is shooting through the thin gold foil here, it should go straight, right? So it should go through it, like what described in picture right here, right? So it should go through it. And the reason for that is because this is the sphere of the positively charged matter, so therefore the alpha particle should just go right through it. However, what he discovered from the experiment is that most alpha particle did not reflect its go through. However, there are some that bounce back or deflect, and the result suggests that most of atom mass and all of its positively charged particles are concentrated in this small core called nucleus, right? And most atoms' volume is empty space through which electrons are dispersed. So he proposed the atomic model that looked like this. This model soon became nuclear atomic model after Chadwick discovered neutron within the nucleus. The nuclear atomic model described the location of proton and neutron correctly within the nucleus, but it did not address the location of electrons, which is the subatomic particles that participate in chemical reaction. So therefore, in chapter 3, we are going to take a look at the electronic structure or the location of electron within an atom. So that way we can see it clearer how electron participate in a chemical reaction. And in this chapter, we are going to take a look at Bohr model and also the current atomic model, which is the quantum mechanical model as well. And these two models come from the study of how light interact with matter. So before we jump into these two models, we will need to first study the property of light. Now let's take a look at the property of light. Light is an electromagnetic radiation, which is the energy that's sent out from atoms and molecules as they undergo change. And these radiation going to contain the electric field and also magnetic field that travel perpendicular with each other, like as you see here. The first property of light that we are going to take a look at is going to be the wave property, which is the repeating oscillation about zero. We are going to use the sine wave function to describe light. Okay, so for example, if you plot between x and y axis, okay, so give y equal to sine x. So if you give x equal to 0, right? What would be the value of y? So if you plug this number into your calculator, you are going to see that the y will equal to 0. And you can use x to be any positive value, okay? So, but I'm going to show you in the increment of 30 for our easiness, okay? So I'm going to increase x to be 30, 90, 150, 180, and so on, okay? So if I do this and plug this number of x into calculator side of this x, right, value, you are going to obtain y value as indicated here. Okay, so if I continue to do that until I get up to side of x 390, you are going to see that there is the repeat wave function, right? So for example, if I plot this, right, so the first one right here, you are going to start at 0. The second one, right, is increased by half, and then the next point you are increased by 1, right? So it's at the top, which is the peak. So if you continue doing this, you are going to observe that this sine wave function is going to look like this, right? So it's going to look like something like this because it's going to go up and down as indicated here. Next, we're going to take a look at the property that come with this wave function. Okay, so the highest point is what we refer as crest. Okay, and then the lowest point would be the trough. And the height of a wave that measure from the maximum point to the 0 point or the minimum point, right, to the 0 point, this is what we call amplitude. If you refer this to sound wave, amplitude will tell you about how loud it is, right? So the higher amplitude is going to represent the louder the sound. For the electromagnetic radiation, the amplitude will tell you about how bright the light would be, right? So the higher or the bigger amplitude is going to represent a brighter light. Note is a point of the wave where amplitude is equal to 0. Wavelength is the distance associated with one complete oscillation, and the symbol that we are going to use for this is going to be lambda. Okay, so pretty much you can measure for one complete oscillation like this, or you can also measure it from one crest to an adjacent crest, or another way to measure the wavelength is from the trough to an adjacent trough. Okay, so it can be with any of those. Okay, so those are going to be how you can figure out the wavelength. Because the wavelength describes the distance, so therefore the base unit of wavelength would be in meter. Okay, so that's the base unit. You can also put the prefix in front of this base unit as well. For example, you might see nanometer, right, micrometer, and so on. Frequency is the number of oscillations per second that pass a given location, and we are going to use the symbol nu that look like V like this, right, to represent frequency. For example, if you are given a location, right, so how many of oscillation that pass through this location per second, that is how we define frequency. Both wavelength and frequency will tell us where the light resides on the electromagnetic spectrum. They both can tell us what type of light that would be. For example, would that light be a green light or yellow light or the ultraviolet or X-ray, right? So we can look at the electromagnetic spectrum, which we are going to see it later, to find what type that light would be, right, according to the frequency and wavelength. Because the frequency describes the number of oscillation per second, so therefore the unit of frequency would be number of cycle per second, or sometimes we're just going to use 1/2, and this 1/2 is the same as hertz. Okay, so that means in this case, whenever you see per second like this, know that it's equal to 1 hertz. Okay, so you can use either. Both of them are interchangeable. Next, we are going to take a look at the frequency and wavelength relationship. Okay, so I would like you to look at these two waves here. So wave N, wave B. Okay, so this one, I would like you to look at which one would have a longer wavelength. Okay, so A or B. The answer is going to be A, right? Because in this case, if you think about this, right, in order, the distance that required for A to complete one oscillation is bigger or is larger or is longer than the one that with B, right? So B only use that much of the distance. So in this case, A would have a longer wavelength. If you're looking at frequency, on the other hand, if you give this as a given location, the number of oscillation pass through this location per unit of time, you will see that the number of wave for B that pass through this given location, right, is more than what A going through that given location per unit of time or per 1 second. So in this case, B would be the one that have higher frequency. Okay, so again, this is wavelength, lambda. This is nu, right, frequency. Therefore, when you're looking at the relationship between frequency and wavelength, they are inversely proportional to each other. And this symbol right here is going to indicate proportional symbol, right? So in this case, it's 1 over that lambda. So it's indicate the inverse relationship between frequency and lambda. Okay, so the direct relationship between frequency and lambda would be through this equation here, which is nu equal to C over lambda. And this C right here is a constant. Okay, so this C is a constant for electromagnetic radiation that travel in vacuum, which is I'm going to call light. They are going to travel with the same speed, which is 3.00 times 10 to the 8 meter per second. Okay, so this is the speed of light. Okay, so it's applied to every electromagnetic radiations. Okay, so for example, if you're looking at red light versus green light, they both are going to travel at the same speed in vacuum. Okay, so which is going to be this number. If you're looking at ultraviolet, right, versus X-ray, right, which is part of the electromagnetic radiation as well, they both are going to travel with the same speed. Okay, so same thing. If you're looking at the speed of X-ray versus the speed of red light or green light, they are going to travel with the same speed, which is this number right here, right, in vacuum. Okay, so again, so this speed of light is going to apply for all electromagnetic radiations. Okay, so note that because this number right here contains 2 units, as we look at the conversion factor before in chapter 1.5, right? So recall that in the previous chapter, you see that the number that contains 2 units, those can be used as a conversion factor. So therefore, in this case, you can use this and write this in a fractional form like this. So that means if you want to cancel time, right, you can put it in this way. So that way second can cancel each other out and you are going to obtain the distance, right? So vice versa, if you want to cancel the distance to get time, in this case, you have to flip it, right? In order for the distance to be on the bottom and time unit would be on top. Therefore, in this case, it's going to be used to figure out time if the distance is given, right? So that means in this case, with the speed of light, it allows you to convert between time and the distance. Okay, so just note that, okay? And as I mentioned before, okay, so this is very important here. All electromagnetic radiations travel at the same speed, okay, and that is going to be this speed of light right here. Why is that important, right? So the speed of light can actually help us determine the distance between the star and our planet. For example, this homework chapter 3, number 4 here. Okay, so in this case, it's giving us that the distance right between Earth to Sun is 93 million miles. Okay, so that's the distance because it's give you in miles. Okay, so it asking us how long. Okay, so this involved with time. So that means, oh, you are given distance and you asking for time and it's involved with light, right? So therefore, in this case, you would need to use the speed of light because all the light, doesn't matter what type it is, they all are electromagnetic radiation. They are going to travel with the same speed, which is this speed right here. So that means in this case, you can connect between time and distance through this, right? So this is going to be your conversion factor. So therefore, in this case, what I'm going to do is I'm going to start with 93 million, right? So million is times 10 to the 6 miles, so mi. Okay. If I started this way, you probably notice that the speed of light that we have is actually given in meter per second. Okay, so this is not mile. Okay, so mile is the mi. So remember, every time that you see the number with the 2 units, you will need to write this in the fractional form. So therefore, in this case, you are going to be, you need to rewrite this as 3.00 times 10 to the 8, right, meter over 1 second. So in this case, if you want your final unit to be time, the second have to be on top, right? So that means in this case, if I put the second on top, I will have meter on the bottom, but the given information that we know here is given in mile, is not the meter yet. So therefore, you will need to convert mile to meter first. Okay, so that means in this case, what you will need to do is you are going to go back to the conversion factor, the list that you learned in chapter 1.5, because those lists going to be given on the exam and you are allowed to use only those lists. You cannot use any conversion factor outside those lists. Okay, so again, in order to get full point, you have to use only what is given on the exam or discussed in class. So in this case, what you are going to do first is going to be convert from mile And one of the given information that you learn from chapter 1.5 is mile to kilometer. So I'm going to go to this, right? So every 1.61 kilometer equal to 1 mile. So I will do that first. Second step would be convert from kilometer to meter, right? Because we want to be in meter according to the speed of light. So in this case, kilo, right, in front of base unit, kilo is bigger than the meter, which is the base unit. So therefore, in this case, the 1,000 is going to go with the smaller unit, which is meter, because it needs a lot of small unit to make it equal to one big unit, right? So the 1,000 would go with the meter. So now if you cancel the unit, mile cancel out, right, kilometer cancel out, so you are going to have meter left. The next step would be then you can use the speed of light to cancel this meter. In this case, if you plug it in 3.00 times 10 to the 8 meter over 1 second, you probably notice that the second is on the bottom. We don't want that, right? So we want how long? So we want second to be on top. We want time to be on top because at the end, time need to be on top, right? That is our final answer. So in this case, you need to flip this, right? So we need to flip this. So that means we are going to get every 1 second is going to require 3.00 times 10 to the 8 meter for light to travel. Okay, so if you check your unit here, meter cancel out, you are going to get second left, but the problem asking in milliseconds. So that means you need to do the final step, which is converting from second to millisecond, right? So I'm going to convert this second to millisecond. So second and then millisecond. Milli in front of the base unit is going to describe something that's smaller than the base unit. So therefore, in this case, it's going to require 1,000, right? Of the millisecond to be equal to 1 second is required 1,000 of this small unit to equal to one of this big unit, right? Bigger unit. So in this case, if you cancel the second, you are going to end up with the millisecond as your final answer. That's exactly what we want because at the end, your final unit, right, have to be on top. So that's exactly what we want, right? We want is in milliseconds. Okay, so all you have to do next is going to be multiply all the top number together, right? And then divide by the bottom number, okay? One thing I want to point out is that to make your answer to be correct, make sure that when you punch into your calculator, just make sure that you actually include this parenthesis right here for the 3 times 10 to the 8. Okay, if not, you are going to get the difference from what I have. Now, if you do this correctly, you are going to get 4.99 times 10 to the 5th millisecond. Okay, so the last thing we need to check is going to be the sig fig. Okay, so we have 2 sig fig from the given information. This conversion right here between kilometer and mile is not exact value, so this contains 3 sig fig. Okay, so 1,000 meter equal to 1 kilometer. So this is going to be exact value because the prefix we defined, right? And then speed of light. So this is not exact. So this come out to be 3 sig fig right here. Okay, so millisecond to second, that would be the exact value. So it's not going to limit our significant figure. Okay, so exact value will not limit the number of sig fig. So therefore, because we do multiplication and division, so therefore the least number of sig fig will determine your final answer. So in this case, your final answer should contain only 2 sig fig. Okay, so if you do this, if you cut right here, right, so 9, you are going to round it up. So therefore, the final answer would be 5.0 times 10 to the 5th millisecond. Okay, so that would be your final answer with the correct sig fig and unit. All right, this would be one of the example of the speed of light that you can use, right, in order to help us to either find the distance or find time. Okay, so the next thing we're going to take a look at later going to be how we can use this speed of light and then associate the frequency and wavelength to it. Okay. Now, before we get into the calculation part, I would like you to actually look at the conceptual problem first. Okay, so for us to understand of this property of wave better before we get into the calculation. So now let's compare between wave A and B. Okay, so in this case, you probably notice that amplitude of wave A is actually bigger than B. Now for wavelength between A and B, right? So if you're looking at this one cycle right here, you probably notice the distance of this one cycle for both A and B, they are equal, right? So that means the wavelength would be equal. What about frequency then? Well, for frequency, if I give this as the given location, the number of cycles that pass through this given location per unit of time, they are equal, right, for both wave A and B, right? Because the number of wave would come out to be equal. So therefore, in this case, frequency of wave A and B would also be equal as well. What does it say about wave A and B then, right? So in this case, wave A and B are the same type of radiation, but different intensity. For example, if we're looking at the visible light, right? So if we see their color, right, they are going to represent the same color, but A is going to be brighter than B. Okay, so how do you know what type of radiation that would be? Well, this is when you need to look at the value of the wavelength or the frequency and then compare that with the electromagnetic spectrum, which we're going to take a look at later. Okay, so in this case, I don't know what it is exactly because the wavelength and frequency is not given. Okay, so we just know that wave A and B would be the same type of radiation. Okay, so if they fall into the visible light, then they are going to have the same color. Now, what about wave C and D? Okay, so the amplitude of C and D would be equal. Wavelength of D is going to be longer than C, right? Because if you think about this, right, so this is take longer to complete one cycle. This is take shorter to complete one cycle. So D has longer wavelength than C. For frequency, if I give this as a given location, you probably notice that there are more cycle of C pass through this given location per unit of time in comparison to D, right? So therefore, C would have higher frequency than D. What does it say about wave C and D then? Okay, so C and D are different radiations, but they have the same intensity. So again, if these radiation fall into the visible light, they are going to represent this different color of light, but the same brightness. Next, between E and F, okay, so the amplitude of wave E is going to be higher than F, and then the wavelength of F would be longer than E, right? And then frequency of wave E would be higher than F. So in this case, it tells us that E and F are different radiations, and also they have different intensity as well. So again, if this would be the visible light that contain color, right, they are going to represent different color. E is going to be brighter than F. Next, we are going to take a look at the equation that we see earlier, the content frequency, speed of light, and wavelength to help us determine either frequency or wavelength. Okay, so in this case, according to this example here, we want to find out frequency. So we want to find out this, right? So it's giving us wavelength. Okay, so it's giving us lambda. Okay, so that means in this case, all you have to do is that you know speed of light, you know the wavelength, but you just need to divide by each other, and then that's going to give you the frequency. So if you plug the number of the speed of light in, and then plug in the given wavelength, which is 680 nanometer, you probably notice that the two units will not be able to cancel out, right? Because the distance of the speed of light is in meter, but the distance of the wavelength is in nanometer. These two cannot cancel each other out. Therefore, in this case, you will need to convert this nanometer into meter first. Okay, so that means if you do that, you are going to get 680 times 10 to the negative 9 meter. This number also the same as 6.80 times 10 to negative 7 meter. Okay, so they both are the same. It's represent the same value. Okay, so it doesn't matter which one it is. Okay, so they both contain the same number of sig fig as well. Okay, so they both are acceptable. Next, we will need to check the unit. Okay, so the distance described in meters, so therefore we can cancel these two. Okay, so we are going to be left with per second. Okay, so 1/second like that. Okay, so you can write as per second like this, or 1/second, or s raised to negative 1. Or because this is per second is the same as hertz, right? So you can also use hertz as well. These are different ways to write the unit of frequency. Okay, so it can be with any of these. Okay, so what does it mean then? It means that per second, this is how many cycles this wave is passed through the given location. Okay, so that's what it means. Again, note that hertz is the same as per second, so you can use them interchangeable. All right, I would like you to pause the video now to complete this example here. And after you finish, then resume the video again. Now let's check your answer together. Okay, so in this case, we are looking for the wavelength. Okay, so wavelength is part of the denominator. Okay, so we are given the frequency, which is this new symbol right here. So in this case, because the unknown variable is part of denominator, so I need to bring this up, right? Because your unknown variable have to be part of the numerator or on top. So in this case, what I'm going to do is that I'm going to multiply both sides by wavelength or lambda. And now you will see that we have the given frequency, right, multiplied to the unknown variable, which is wavelength. So the next step that I'm going to do is I'm going to divide both sides by the frequency to get rid of the frequency so that the lambda would be by itself. Okay, so if I do this, I'm going to get lambda equal to C over frequency, right? So again, this is going to cancel out, right? This is going to cancel out. So eventually going to get speed of light over frequency. So after I do this, then I'm going to just pretty much plug in the value of the speed of light, right? Divide by the given frequency. Okay, so remember this is per second. This is also per second. So these two are the same. So we can cancel each other out. So therefore the wavelength is going to come out in meter. Makes sense, right? Because wavelength is need to be in the unit of length. So therefore in this case, it's going to come out to be in meter. Okay, so you can leave it like this, or you can actually move the decimal point if you want to, right, to another acceptable value would be times 10 to negative 9. It's the same identical value as this, right? So either way is correct to me. If the problem asks you further for you to convert this into nanometer, you can do that as well, right? So 10 to negative 9 is the nano prefix. So you can actually represent this times 10 to negative 9 with the nano prefix, right? So this can also be reported as 414 nanometer. Now let's take a look at what type of color of this light in part 3A. Okay, so what would that be? Okay, so in order to figure out what type of light, as I mentioned before, we will need to look at the electromagnetic spectrum. So show here is the electromagnetic spectrum. Okay, so this is the wavelength. Okay, so report in meter. Okay, so it's reported in meter. And it's ranging from 1,000, right, scale all the way to 10 to negative 12, which is really, really small. Okay, so that means in this case, you probably notice that the radio wave, right, is a lot smaller than, like gamma ray, for example. Okay, so as I mentioned before, the wavelength will tell you what type of radiation are the same as frequency as well, right? So in this case, if you're looking at the number that we see earlier, right, so it's in, because this scale is in meter, so therefore I need to looking at the meter scale here. Okay, so it's within the 10 to negative 7. So therefore, in this case, if I go back here, right, so 10 to negative 7 would be within this range. Now, in order to see this scale better, I'm going to zoom this in, right? So if I zoom this in, it's going to be within the visible light. So if I'm looking at the visible light range of the wavelength is report in nanometer. So therefore, in this case, I would need to use the nanometer number right here to look at from the scale. And the 414 would fall into with the violet, right? So therefore, the answer of this would be violet. Before we move to the next topic, I would like to actually talk about the electromagnetic spectrum a little bit more. So according to this spectrum, right, you probably noticed that the radio wave, right, going to have longer wavelength than the microwave, right? Microwave would have longer wavelength than infrared. Infrared have longer wavelength than the visible light, right? Visible light has a longer wavelength than ultraviolet, and ultraviolet has longer wavelength than X-ray, right? And then X-ray have longer wavelength than gamma ray. Okay, so that's kind of like the broad region that we can break them into. Okay, so as I mentioned before, the wavelength is going to be inversely proportional to frequency. So therefore, in this case, if you compare the frequency, gamma ray would have the highest frequency, radio wave would have the lowest frequency. We are going to talk about the energy later, but just note that the energy is going to be inversely proportional to wavelength as well, but it's going to be directly proportional to the frequency. So in this case, makes sense, right? Gamma ray and X-ray, they are going to have higher energy than the microwave and also radio wave, right? So that makes sense. You already see the property of light as wave. So the next thing we're going to take a look at is what proof that light behave as a wave then. Okay, so the first experiment would be the diffraction. Diffraction is a bending of wave through barriers with slit. For example, as you see here, right? So in this case, light can actually bend through this barrier right here, right, with the slit to go to the other side. Right, so this diffraction pattern actually confirms that light behave as wave. This is similar to the sound wave, right? For example, if you talk loud enough inside your room, right, people outside your room, even though you close the door, still be able to hear it because your sound wave can bend through the barrier with a small crack of, like the door or whatever, and that bending of sound wave can eventually get through that door to go to the other side for the people outside your room can still hear it. The second experiment that confirmed that light behave as a wave is interference. Interference results from when wave bending through the barrier with multiple slits, and those waves that bend through the slit, they will interfere with each other. There are two types of interference. One is the destructive interference, and the other one is the constructive interference. Destructive interference would come from when the wave have the opposite phase. When they combine, they are going to cancel each other out, and that is going to result in the dark spot on the interference pattern like this. Okay, so for the constructive interference, those are going to be when the wave have the same phase, they combine with each other, they are going to amplify each other. They are going to make brighter spot on the interference pattern. The take-home message of this chapter section is going to be you will need to know the property of light as wave. You will need to know the relationship between frequency and wavelength, right? And also the speed of light as well. And the two experiments that confirm that light behaves as wave would be the diffraction and interference. Please start working on your paper homework chapter 3, number 1 and 6. Okay, so that is going to cover this chapter 3.1.